Thank you very much for this opportunity to talk about the second type of research that we are doing with maybe it's not open. Thank you. Sorry. This is work that Safa Montessori is a student that got 2 PhDs in this area, and Jorge Rivas, who happens to be my son, but he has all his life been interested in this problem, so we are working together very nicely. This is based on several papers that have become quite popular, and I will discuss them. Okay, sorry. 9. Yeah, sorry. I don't know why I am nervous. Yeah. Sorry. So it is clear that the human system is dominating the Earth system, and that climate models must include bidirectional coupling of the human and Earth systems. But that's not what's happening now. So we have published several papers on the Earth and the coupling of the Earth and the human system, and I will present some important results of them. And again, this is work of Safa Montessori, Jorge Rivas, and me. One paper that is very useful because it gives a lot of information is called Modeling Sustainability, and that includes population, inequality, consumption, and bidirectional coupling of the Earth and human system. And this was published, co-authored by about 20 co-authors, and many of them are very famous, like members of the Academies of Sciences. And in this paper, we created this figure, which is it is very powerful. It compares the evolution over the last 10,000 years, so since the beginning of agriculture to the current time, and it plots the population and the carbon dioxide, methane, and nitrous oxide, which are the 3 strongest greenhouse gases. And you can see that during this first 8,000 years or so, both the population grew up very slowly, and also the greenhouse gases, and there are people that think that during this evolution after the beginning of agriculture, the human system already started to slowly change the atmosphere and the nature, and it's shown here. But then at the beginning of the Industrial Revolution, which is about 1750, they just all explode, and it is a very clear demonstration that the population is what's driving the increase in greenhouse gases, unless because it's impossible to think that the greenhouse gases would drive up the population like this. But if we look at the last 2 or 300 years since the Industrial Revolution, we see that there was a strong growth. This is expanded, but then in 1950 there was a second revolution, the Green Revolution, which increased made the population and the greenhouse gases grow explosively. And we can see here the chart from IPCC that shows how CO2 emissions exploded after the Green Revolution. Like here, that's when the Haber-Bosch nitrogen fertilization led to the Green Revolution, and we have this enormous growth of CO2 and others. So in this chart we plot both the population in red and the GDP per capita in blue. And it is over the last 2,000 years, and we see that both the population and the GDP per capita are exploding in the last 200 years or 150 years. And it's very important to emphasize that the impact that the population has on nature is the total human impact is the product of these two. So it's growing at an incredibly fast exponential growth, and I always remember the husband of my niece, who is an engineer, looked at this figure, and I said, whenever I see a figure like this, I know that there's going to be a collapse soon. So it's very important. Here is the population and the GDP per capita year by year over the last 50 years. In blue is the GDP per capita, and it's more variable, but on the average they are about 2% per year of each of them. This was a big drop in economic drop in 2009, and it is the product of the two is about 4%, and so this is that the impact that the human system is having on the natural system in nature is growing, is doubling every it's doubling every 18 years or so. So we are doubling the total consumption of nature that we make every 2 decades. And on top of that, it's very important that we have inequality. For example, in the greenhouse gas emissions, 10% of the population produces about 50% of the emissions, and the 90% produces the other half. And so the wealthiest 10% of people produce about the same emissions as the poorest 90%. So raising, if we think life should be fair and everybody should have access to consumption which is similar, if we were thinking of raising the bottom 90% to raising the consumption to match the top 10%, this would require increasing the total emissions by 5 times, so we should have 5 times more gases. So it's impossible. So what is the real relationship between the human system and the Earth system? Here we have a schematic, and the schematic shows that the human system is within the Earth system. And the Earth system has sources that provide the input, like energy and material and water, to the human system. And the human system has components and sectors that after it uses the inputs, it produces outputs, which are garbage and like emissions and waste and land use changes. And the garbage goes to the sinks that the Earth system gives us, which is the atmosphere, the ocean, the land, aquifers, lakes, rivers. So we have to think that everything that we do is within the Earth system. So the human system outputs must be absorbed by the sinks. No. So that's necessary. In the past, let's say before the Industrial Revolution, we had a human system that was very, very small compared to the Earth system. So it had inputs which were very small compared to the sources, and outputs which were small compared to the sinks. And so we could model the human system and the Earth system separately, like we are doing now. But now things have changed a lot. So the present is a full world. The human system basically is covering the Earth system, and so the system should be model coupled to each other like they are in reality. Now, human system inputs and outputs are so large relative to the Earth system that they threaten to deplete the sources and overwhelm the sinks of the Earth system. This is a figure adapted from a well-known IPCC graphic showing how Earth system components have been developed and then bidirectionally coupled over time. And in the mid-1970s, when I was a student, the Earth system model was the atmosphere. That's it. Then in the mid-80s, the land surface was coupled to the atmosphere, and then at the end of the decade, Kane and Zibiak developed a coupled ocean-atmosphere model. So this was added to this. And so until Kane and Zibiak developed an atmosphere a coupled atmosphere-ocean model that was bidirectionally coupled, it was impossible to predict El Niño, and it was tried by several people and they couldn't. But when this allowed the coupling of the atmosphere and the ocean, bidirectional coupling allowed to predict El Niño, and now we do it not normally, but without having the atmosphere be able to change the ocean and the ocean change the atmosphere, we could do that, because you you need bidirectional coupling among the atmosphere and the ocean, like in reality, and that produces El Niño. But now we are the most important subsystem, which is the human system, is still missing from this long list of components that are being added and making the system, the natural system, more complete, but not the full system. So the human systems have not been bidirectionally coupled. So this is the figure that we had before, and all of this representing the human subsystem models is missing. So this is to model climate and climate change. We argue that it's necessary to include the human system and a measure of how stable and in good shape it is, which is the current capacity. So we about 15 or 16 years ago, no, sorry, 6 years ago. Yeah, in 2014 we published the paper that it's actually becoming more popular, more and more popular, more than 350 citations. We, both Safa, Jorge, and I thought that we should do a minimal coupled human and natural system coupled, so we call that human, sorry, we call that human and nature dynamics of Hanley model. And I am happy to say that I contributed something very important to this model, which was immediately thought we should include inequality, the fact that we have rich and poor, and indeed that's very important. So the title is Human and Nature Dynamics, Modeling Inequality and Use of Resources in the Collapse or Sustainability of Societies. And before I read our paper, I then wasn't aware that there have been like thousands of major collapses of civilizations. In some places happened again and again. And this is basically what the model shows using birth rate and death rate and similar to observe. So if we have a variable which is nature and it starts completely saturated, and then we have the commoners, which are the poor that work, and when the population starts growing and wealth is accumulated, because with agriculture, for example, for the first time you could save rice for the future, and that was the first time that we could accumulate wealth. So the wealth which is accumulated by the rich increases, and this carrying capacity represents the steady, stable population that the Earth can maintain using regrowing nature. So, for example, fish regrow or crops regrow, and that's all the system the nature has. So, as things look like they are going well, but as soon as the majority of the population, which is the commoners, crosses the current capacity, we see that the wealth starts to decay, and then the elites, the rich people who make 100 times more in our model than the poor, continue growing, but by sorry, but by as time goes on, the commoners are growing, continue growing, and so are the elites, but the elites consume much more than per capita than the others, and then there is not enough food to feed the poor, but the rich think, wow, things are going great, we are growing like crazy, and then they also run out. There is a complete collapse, like it happened many times in history. So this is an unequal society. So over-depletion of nature, overuse of nature, and over-exploitation of the poor lead to irreversible full collapse, in which nature collapses, everything collapses. And here are other examples. These are egalitarian societies, so there are no rich and poor, they all make the same amount. And in this case, if the consumption of nature is not excessive, then the system reaches an ideal equilibrium in which nature is half of the saturation, which allows it to grow fastest, and the population reaches the current capacity, and the wealth is sufficient, and it continues forever. And there are, when we increase the consumption of nature, instead of this ideal result, we get oscillations, and then it converges to much lower values. And if we increase the consumption even more, there is collapse. And in this case, we have a situation that starts exactly like this, except that we added a very few elite, rich people, and until about 500 years, it doesn't matter, but then they grow, as they grow exponentially, and then they may collapse the whole system. And another, we did several, many examples, but a very important result is that if we, instead of having only a nature that regrows, for example, fish or vegetables, so that it is renewable. We add fossil fuels, which are non-renewable, and we add a large amount, like we are using a large amount of fossil fuels, and this was the collapse in the one example that I showed before, and the collapse happens at about 500 years. And now we we use both the regenerating nature but also the non-renewables like fossil fuels that we added. And the result is that the collapse is postponed by about 200 years. And very, very, very importantly, the population increases very fast, but by a factor of much more than 10. And this is exactly what happened after the Industrial Revolution, when we see that those growths, very fast growth, is because basically we are eating fossil fuels, using. And the use, those fossil fuels took hundreds of millions of years to accumulate, and we are getting rid of them in 200 years or 300 years, so it's hundreds of millions faster than it was created. So humans also impact climate change through land use change, and for example, we used our reanalysis to give a measure of how much of the change in use of the land, like agriculture, affected the emission of temperature, and other studies. So I want to give an example which is much more encouraging than what I showed so far. So how land use change can impact climate. It's in a paper that was published in Science, and it was published in Science, and within 3 weeks it was downloaded more than 100,000 times, and it reached number 30 out of 50 thousand papers in all the sciences. So the paper was Climate Model Shows Large-Scale Wind and Solar Farms in the Sahara Increased Rain and Vegetation. Not only energy, and these are the authors. And we modeled how solar and wind energy infrastructure can affect the climate conditions in the Sahara and the Sahel, and in particular precipitation. And so it got rated very highly, but like in the top climate papers of 2018 and in the top 100 of all science papers, the medical papers, which is Brazilian. So I have the idea, original idea of this paper, because I remember that Charney, my advisor, Jules Charney, was very impressed with the horrible reduction of precipitation that was in the 50s and 60s and 80s and 90s. There was a very strong reduction of precipitation in the Sahara, and especially the Sahel, and so what I thought is we could use the same ideas that Charney had, and also Yogesh Sood had, to explain the reduction of precipitation. And what Charney said was, in the Sahara, the albedo is very high. There is a lot of reflection of heat, solar heat, so the heat goes up and then the atmosphere compensates by going down, and that stops precipitation. And I thought, what could we do which is the opposite? And if we put black solar panels all over, the albedo is reduced, and that should increase precipitation. At least I hope that. And similarly, the idea that Yogi Sud had was that sorry, I missed to say, Charney attributed the increase of albedo to the overgrazing, that the animals, the population was very high in the Sahel, and the animals were too many, and they were eating the vegetation, and that increased the albedo and reduced the precipitation. And Yogi Sud said, if you have overgrazing, eating too much the vegetation, then the surface is much less rough. It becomes smoother, and therefore there is less convergence, and therefore less precipitation. So I thought, what if we put windmills over here, which obviously increase the surface friction a lot, and therefore they should produce convergence and upward motion and rain. And what if we put lots of solar panels and it becomes dark, so it absorbs heat, and that moves the atmosphere up, and that increases precipitation. So we performed an experiment with a speedy model to which Ming-Zel added vegetation which is dynamically dependent on the climate, changes with the climate. So, what are the impacts that we would have if we put solar and wind panels in the Sahel? What would be the impact on the climate? The global climate would be great, because it will immediately allow us if we put solar panels and windmills in the Sahara, they increase the production of energy, so that there are 4 times as much energy as used for anything. And the current human system uses less than 1/4 than what we could produce in the Sahara. So, the global impact would be great, because we would stop right away reduce immediately to very low values greenhouse gases emissions. But how about the local impact? It's good, bad, or it's an example of geoengineering that in most cases is horrible. So we had to do this experiment, and this experiment was done inspired by these 2 or 3 decades of low precipitation. And here we have a picture that shows the albedo and we see that the Sahara is not only the largest desert, but also has the highest albedo. So basically we covered the Sahara wind and solar farms. And this is again the mechanism that Kalnay and Sud have developed, saying overgrazes increases albedo, less heating, downward motion, less rain, less vegetation, and the less vegetation increases the albedo further, and this is a positive feedback mechanism, and same with reducing friction. So what we want to do is the opposite, and this shows schematically that if we put wind farms, increase surface friction, this increases low-level convergence, increases precipitation, increases vegetation, and the vegetation further increases the. So we have this feedback, and same with the solar farms. If we cover the desert with the sun with solar panels, the albedo decreases, and as a result the surface heats more, and there is upward motion, and that increases precipitation. So this is what we were hoping, and we used a model that has an atmosphere and land surface and dynamic vegetation that changed when the climate changed. And so we published this paper, climate model shows large-scale wind and solar farms in the Sahara increase rain and vegetation, and it was quite popular. And this is the basic result. We have wind farms and solar panels, and then wind and solar. And here is the temperature change, and here is the precipitation change, and the temperature increases by about 3 degrees on the average, and the precipitation increases quite a lot. Actually, in the Sahara it increases by about 1 millimeter per day, but in the Sahel, which is the southern part of the Sahara, it increases a lot. And 80% of the precipitation impact is due to the dynamic vegetation feedback, which shows the importance of bidirectional coupling. So, and we found that if we don't put it everywhere, but let's say in 1/4 of the Sahara, the northwest produces almost as much precipitation as the whole Sahara. And for a reminder, where this is the Sahara Desert, and south of that is the Sahel, which is a band, which is where the poorest people in the world, and ones that try to emigrate from there, live, and also they have the highest procreation in the world. And very, very sadly, this is the main lake that they have is around here, and the lake has been decreasing. Lake Chad has been decreasing with time. So by 2007, it had essentially disappeared. When in our system, the impact of putting solar panels and windmills was to increase the precipitation, especially in the Sahel, and the total maximum, it's exactly on top of Lake Chad. So precipitation in the Sahel increases up to 500 millimeters per year, with the maximum in Lake Chad. And the increase in precipitation is larger than the decrease that took place during the drought. And and perhaps the most important thing is that these solar panels and windmills would produce more than 4 times the total energy used by mankind. So we don't need fossil fuels. And the Sahel is the poorest region in the world with the fastest population growth, more than 7 children per family. And it has the largest emigration and the largest deaths in the world. And the UN population projections estimate emigration will go to 0 because they could not estimate how it will evolve. So the climate models also, when they simulate the migration, they make it 0. So we have developed a schematic of how to couple the Earth system with the human system, and this is a schematic of the bidirectional coupling that could be used in a coupled system. So it's complicated, but it's not horribly complicated. It's very important that it has a human system, that the human system includes itself the population demographics. They don't come in a table, they are computed by the system, and fresh water, and it's very, very important to include these things. But one thing that is super important is policies. So the policies of the government have to be good policies. If they are not, it doesn't work. And many people think, oh, the government does everything wrong. Only the private sector knows how to do things. So I just thought I would show you. Oh. I will show you one map that when I saw it amazed me. This is showing the South America, and here is Argentina and Uruguay and Brazil and Paraguay and Bolivia. And in this map, the red indicates the highest possible NDVI vegetation index. So a full red means 100% saturated of trees. And when I saw this, I couldn't believe it, because this is clearly one little province in Argentina, and it was completely different from all the surrounding areas. So I called my friends, I talked with my friends and asked them what had happened, that this Misiones province, little province, not powerful at all, who have saturated trees and forests, and they told me that the government had realized that the main source of income was the forest, and so they put laws that allow to exploit the forest, but only up to 30%. The rest, 70%, is protected, and also the part that's exploited has to be renewed, and it just worked. So if we had, for everything that needs laws to decide how to use it, every resource from nature, that if we had a local government that protected it, we would be better off. And so this is my last slide. Thank you very much. Wow, I thought nobody was coming, but okay. Thank you.
We'll take some questions.
Okay.
Okay.
You want to?
Yeah, there was another mic. Let me see.
Voice got stronger.
Huh? This one
Do
maybe?
you have another
Another
mic?
mic? Oh. Any questions to Eugenia?
Your wind and solar plants experiment is a very interesting experiment.
Sorry.
Okay, solar and wind
Yeah.
plants.
Yeah.
It's a very interesting experiment.
Yeah.
So it is very good to know that the Sahel and Sahara are getting better. But what will happen to Indian monsoon?
I am ashamed to say that I don't remember. I looked at it, but I don't remember what it showed. But it was not clearly different.
It's not
Yeah.
different.
But for example, the